Welcome to database normalization, everyone. We're going to be talking about database normalization and good design. And I think that I've presented this at a few other places before, and it was really just before the last time I presented that I realized how tied database normalization is to design. And so and it wasn't until last night as I was re-reviewing my slides that I realized that I changed the title. So if you saw the subtitle, so if you saw a previous subtitle because you looked at the schedule a week ago, it's changed. I think that this title is more accurate, but if you loved the old title and that's why you're here, we'll be doing some of that, though less than I was anticipating. Oh, did I lock it? If you want some more of that, that's totally cool. We'll dig in and we'll have tons of time. We'll have some time for questions at the end, and we'll see where things go from there. I'm McKay. One question you might be asking is, why should you listen to me? And the answer is, that's up to you. I'm not going to insist that I'm always right. And in fact, if you think I'm wrong about anything, I definitely want to know. But I have been working in databases since most of you were born. I built a relational DBMS and I helped build this data4 thing we were talking about, I think before some of you were born. And that makes me feel a little bit old, but that's okay. I've been doing DBMS stuff, and especially relational databases, for a long time. And this started because I've been doing a lot of database work, and it feels like only recently have I fully grokked normalization. Like, when I was taking database classes in college, I passed the test and I got an A, but it didn't really grok it. And it's kind of only been recently as I've seen more and more databases more and more databases, and I mean that different from DBMSs, more and more databases that suck. Your favorite DBMS sucks. Your favorite database probably also sucks, statistically speaking. Like, I've worked with some really, really smart people, and almost all of their databases suck because they don't understand good design. And some people have a pretty good grasp of design, but not database normalization. And so that's what we're going to get into more than anything else. And if your database at your company sucks, let me know, and I'd love to come help you out, because I'm available for contracting work, and I find this stuff fascinating and I love it. So give me a call. So this is the plan for today. I like using code. This is some pseudocode. This is, think of it as Delphi or Pascal, Object Pascal, or D4 if you like. They're all very similar syntaxes. But so I shouldn't focus on the syntax here. You guys understand pseudocode even if you don't understand the specific language. We're going to be talking about design and normalization, what that really means and why they're tied. Then we're going to talk about the French invasion of Russia, and I promise it's relevant, at least a little bit. We're going to align on language, teach the basics of what's going on here, and then go into detail about each of the normal forms for various levels of detail. We're going to focus more on the first few and gradually taper off and almost not, and only mention like 6 in passing if we get there. And then we're going to talk about what that means and where we go after here. So, you guys have heard the term design. You guys think about design. And I've recently been reading Zen and the Art of Motorcycle Maintenance, and he talks about quality in, I've been loving that book. I'm not finished with it yet, so no spoilers. But good design is about best practices and doing things that work well, building software with quality. And in the world today, there's lots of different types of design, and this is not an exhaustive list. But when I'm driving here on the freeway, I can drive anywhere across the country and get there even without a map because of sign design and how the highways are organized. And some states do better than others, but the federal highway system is brilliantly designed, in my opinion. But even if you don't agree with that, you can at least agree that there is good design and bad design in highways. And the same thing could be said about interior design or industrial design. There's lots of user interface designers, and that makes sense too. And then there's slide design. You may hate this slide design. When I was making these slides, I went to Google templates and I was like, ooh, that one looks cool. And then I started it and I started using it, and the more I spent building this presentation, the more I decided I hate this design. But I didn't want to change anything, and I was lazy, but I could use it to talk about design. I'm curious at the end if you guys think this template design sucks. It's not. I didn't make it. I kind of think it sucks. We're going to talk about things that suck today a lot. And so what is good design and what is bad design is something that people generally know, but it's hard to quantify in a lot of cases. And Zen in the Art of Motorcycle Maintenance talks about how it's hard to prove what good design is. And he's wrong. But in order to prove why he's wrong, we're going to go back to the 1960s. In the 1960s, there were software engineers. Not many, and they mostly had these big $1 million computers, but there were software engineers, and they were building data systems. And in many ways, it was the Wild West, and their design sucked. And sucked in ways that just before we started, I was talking, I've worked with a lot of databases that suck, and these are a lot worse. So much so that there were lots of papers written about why they sucked. And we could talk about all of these things in detail, and I'm going to go into a little bit more of them in some detail later. But there were lots of reasons why their databases sucked. And they talked about it formally and could realize, that, they proved why some of these databases suck, which is what I'm going to say is the counterproof to Pirsig and one of our meetings. But what happened is a guy named Edgar F. Codd came along, and he was working with some of these databases, some that he wrote and some that he didn't write, and he had degrees in mathematics, chemistry, and computer science. Yes, even in the 60s, computer science was a degree, and he had an advanced degree in computer science. And he looked at this, and he saw how bad the database design was, and he thought, you know what? Math has been around for a really long time. And it has been. And mathematicians have spent a lot of time building up a lot of knowledge about numbers, and information theory was still kind of new, but numbers were a lot of what was being stored in databases anyway. And so he decided to take the mathematical principles of things. Mathematics had been used for thousands, if not tens of thousands of years, and set theory was also very old, relatively speaking, from a computer perspective. And so he decided to apply these mathematical principles and rigorously attach them to databases. And so he came up with what is now called the relational model. And if you guys have heard of a relational database, it's not a relational database, almost certainly. But when you've heard of a relational database, it's referencing what he came up with in the 70s. But more important than that, because the relational model is built upon centuries, if not millennia old mathematical principles, we could apply the math the thousands of years of math to our data and prove what makes things good and not. And so I talked about design a bit earlier, and good design is kind of hard to really quantify, and Pirsig talks about that as well. Maybe he comes to a better conclusion than I know. I haven't finished the book yet. But being able to formalize design, I personally think is really cool. I have no idea whether or not slides are good or not. I hate this slide set now because I've been staring at it too long, or maybe because it's actually bad, I don't know. But with the relational model, we can write formula that prove design is good versus bad in at least some areas. So I think that's really cool. And so everybody should normalize, and you really should. It really makes a difference in the quality of the software that you build. And I am going to point out that yes, there are some people who think that sometimes you might want to denormalize for performance reasons. I think that in modern software architecture, that's less true than it was in the 60s, and it's less true than it over the course of time. We have other better forms of optimization than database denormalization. I'm probably not going to go into that too much more, but maybe we'll have time to talk about that at the end if y'all are still curious. But don't denormalize. As a good rule of thumb, don't denormalize unless you have a really good reason. Okay, so Russia. I was not a history student. I have taken a few history courses. I heard about Napoleon and Russia, and these are all things that I'd heard about, but even when I was in history classes, I didn't really fully grok why Napoleon was a bad, what happened, what was the fall of Napoleon, and they talked about it, I didn't really grok it. And after I had graduated from college, I saw this map. This is a map by Charles Minard, and this is one of my favorite maps of all time. And I love maps, I'm a map head, but this map, even in French, this is a French map that he made, still taught me more about the fall of Napoleon than all of my other history courses combined. And it may take a little bit to understand, but this is a two-dimensional map. It's a map like with things here. There's a city in Poland over here, and Moscow is all the way over here. You can read Moscow if you squint, if you see, oh God, that's Moscow. I don't really know what Horno is. It may be a real city in Poland. That's not important. But the thickness of these bars represents the strength of Napoleon's army. So the orangish thing is the advancement to Moscow, and the black is the strength of the army on the way back. And now that I've told you that much, looking at this map tells you everything else you need to know. That Napoleon lost. He lost big. His army was decimated, I believe is a pretty accurate term here. But his army got destroyed. But it wasn't in Moscow. Moscow isn't where his troops lost. They turn around and turn tail, and the strength of the army was just barely diminished in Moscow. But Napoleon lost, not because of any wars he was fighting, but because of the temperature. And so this map presents a lot of information in a very dense and concise format. And yeah, it might be helpful if you could, like, you guys didn't know that this was temperature if you didn't speak French or if nobody else had told you. But this map presents so much information in a very compact fashion. So I consider this map one of the best maps with respect to design that I've ever seen because of how compactly it presents the information and intuitively. Once you've seen this format, you could then apply that to any other number of armies advancing across anywhere, and then this format could be used to help explain where losses occur. This is a format that I think war historians or whatever should be using because of how intuitive it is. And then once you've seen this format, you can apply that to other maps, and that can help you grok things more quickly. It took me a little bit longer to grok it than the first time, or I had someone explain it to me. But then when you see other maps, it'll be like, oh, well, that was interesting. These guys did lose at Gettysburg, or whatever else is going on. So I think this format is very powerful. And so I want to, because I'm talking about databases and database design, I want to talk about a diagramming language that is good for databases. How many of you have seen database diagrams before? And how many of you have seen database diagrams and it's taken you an hour to understand them? And if you've worked in big legacy systems, I can see based on what I'm guessing is the average age of this population, some of you haven't worked in really big systems because you're still in college or whatever, and that's cool too, but maybe you've seen database diagrams, and almost all of the database diagrams I've ever seen suck because it's so hard to understand how they work and what all the relationships are between all the different tables. And so I'm going to present a database diagram here, and it's called the Alphora style. And there are only 2 rules in the Alphora style system, and one of them is optional. The first rule is that arrows indicate the direction of the reference. And this rule is optional. I recommend it anyway. You can just drop the arrowheads, but I recommend keeping the arrowheads because it makes a lot of sense. So we've got 2 tables here. We've got the department table and the employee table, and I'm not going to design what these tables actually look like because you guys know how to read a database diagram, hopefully. But there's a couple of columns here and a couple of columns here, but there's an arrow pointing from left to right, and the arrow represents the direction of the reference, which, if you're familiar with SQL, is alter table employee, add foreign key, alter table employee, add foreign key department ID, references department ID. You guys, if you understand this, then you can see what this arrow means. And because the arrow is pointing to the left, these things reference things here. If there's something in this column, there has to be something here for that to make sense, and that's where a foreign key is. I'm not going to delve deep into foreign keys today, but if you use the arrow that means this, then just because there's a bunch of other arrow notations, and I hate almost all of them. Like if you guys have seen the crow's foot notation, it's hard to think, okay, well, what do the three things mean, and the circles and the lines? And if you stare at enough of them, then you'll eventually remember. But if there's something really simple, it's going to be easier to grok. And also, what's the difference between 0 to 0 and 1 and 0 to 0 or 0? Or 0 to 1 and 0 to 1 or 1? You know, like, what is the difference? Most DBMSs can't even distinguish between them. The diagram somehow does. And do you really trust that the engineer knew what they were doing when they were drawing all of those? In my experience, the answer is no. A simpler design system actually makes sense. If you've got somebody who's a professional database design diagram and they're doing that all the time, then they're likely to make better database diagrams. But most of us don't spend all of our time in database diagrams, so we want a simpler system. And so now I look at department employee, I see the arrow, and it's like, okay, employee references department, that's a one-to-many relationship. And I know that just quickly, like the Menard thing we were talking about, that being able to see this here makes me quickly able to understand what's going on. The second rule is about the direction. And so in this case, we have the student table, and the students table is still referencing the person table. And so that's still the same. We've still got the references because that's what the first rule is. But the second rule is the direction indicates the uniqueness of the relationship. In this case, the person ID references the person table person ID. And person ID is a key here, which means it's going to be unique. And because this is unique, the arrow is going up, and now we have a one-to-one relationship. And it could be a 1-to-1 or a 1-to-0-1 or 1-to-1-to-1, and all of those different rules. We're not getting into that. We're just saying that it's a one-to-one relationship. And because it's pointing up, you can see that it's a one-to-one relationship. And so if it points to the left, it's a one-to-many relationship. If it points up, it's a one-to-one relationship. And just by doing that, those two simple rules, it makes your database diagrams a lot easier to read. Oh yes, 1-to-1, 1-to-0-1. A person may be either a student or a teacher, and I'm not going to say that a student can or can't be a teacher. This design doesn't tell us that. But because there's both of these two things, a person could be a student and a person could be a teacher. Whether or not they could be both, we don't know based on this diagram, but because we see these two things here, we can say, oh, it's much more easy to grok what these things are, even if you don't even have what these columns things are. Some database diagrams I've seen don't even have the columns because they're just trying to present a simple, they're trying to present the relationships at a higher level because the details don't matter. So I can show you this, and even without listing what any of the columns are, you can see the relationships once you're familiar with the design diagram system. We've got person, director, and actor, movie actor, movie director, and we can see this, and the way in which the data is organized with things being left and up and down help you more easily grok what your what your database schema looks like and the relationships between the tables. So this is why I love the Alphora style database diagramming. And those are the two rules. It's simple. Even if you're at a company and they don't have this as a standard, get it adopted as a standard. But building your own diagrams and make in this way will make it so that you can more easily come back to understand them later. And if you teach it to other people, or you ask me to come teach it to them, then that will make the things easier to understand. We want to use Menard's power of compacting and making these tables easier to understand in what's going on. Yes.
Well, so you were distinguishing between vertical and horizontal.
Yes.
Can you just repeat what's the meaning?
Yeah. So because this arrow points up, it's a one-to-one relationship. Okay. And because this arrow points to the left, it's a one-to-many relationship. So a director has been on many movies, but a person can't be more than one director. A person can't be more than one actor. They are either an actor or they are not an actor. So it's a one-to-one relationship here, but this is a one-to-many relationship. And it doesn't really distinctly matter the direction indicates the uniqueness of the local part of the foreign key, but notice here, this goes up, but because this comes out of the left side and comes into the right side here, sometimes you get things where, like, because of how complicated the tables are, which is a smell in my opinion, I haven't formalized that yet, but sometimes you have to move things around in different places, and so you've got these arrows going around, and as long as it comes out of the left side here and goes into the right side here. It's a great question, thank you. Okay, so now we also need to align on terminology. I've been using some terms, and I've been intentionally ambiguous about using the terms, and maybe you have or haven't been paying attention, and that's cool. What we have here, this is a table. Everyone can understand that this is a table. My mom, who is not technically inclined, knows this is a table. This is literally an HTML table, and I didn't apply any CSS to it. So it's just a table. And I'm going to use this as a reference, and we're going to talk about this in a lot of different senses here. But if you're familiar with databases, you might see, oh, this is a table, and you might be thinking of a database table, and I don't mean that. A table is an arrangement of data, particularly with rows and columns. I think I pulled this from Merriam or some dictionary, it doesn't really matter. It's an arrangement of data with rows and columns. This, my mother would recognize as a table because it's in rows and columns. And when I say table, that's what I mean. It's an arrangement of data, particularly with rows and columns. You guys know what a column is. It's a vertical arrangement of items, and a row is a horizontal arrangement of items. This makes sense. Everyone should understand this. My mom understands these things. And I'm sorry, I didn't mean to be talking down to anybody if you don't understand. It's okay, but I want to make sure these terms are abundantly clear, because if you don't understand all of the terms on this page, we're gonna have a hard time understanding things later. So please, I'm sorry if I was disparaging in this last section. My mom understands them. She's a smart woman. If you don't understand any of these things, please ask, because we're not going to get very far, and you're going to get lost if you don't understand all of these terms. So please ask. So a set. This is a math term. If you've spent time in math, if you're a mathematician at all, or if you remember, they talked about this a little bit in junior high math for me. This is a term that my mom, I don't know if she knows or not, but people who are mathematicians do understand this term. It is an unordered collection of unique values. And we're going to talk about this maybe a little bit more later. But again, if you have any questions, please ask. A domain is a term that's used in database theory and in math. And a domain is a classification of valid values. And it's kind of like a data type. People in the database theory world will use a slightly different definition than data type. There is a distinction there. I'm not going to go into a lot of difference. If you like making sub-data types of string, then you're really on the right track, and that's a lot closer if you do that. But if you don't, then domain may not be there's a distinction there. Domain is about a data type. We're still good with everyone. I'm not seeing any confused looks, but please raise your hand. The next thing is a variable, and we are going to talk more about variables later. But a variable is something that can hold different values, and the values change over time. And as I think most of you are here at a data conference, you guys have heard of variables, you know what they are, but we're going to get really deep into variables later. Next is a heading. Now I'm getting into very much database theory types of things that if you haven't heard of, don't feel bad at all. This is what you probably learned in the 400 level computer science course. We're gonna keep it down to 100 or 200 level, hopefully, but if the heading is a set of attribute names and corresponding types. So we've got a table up here, and if we're gonna think about this like a relational table, which is not really the same thing, but this table has a heading, and I literally used the TH tag in HTML to generate this row here, and that's why it's bold and centered. I applied zero styling myself. But it's got a heading here. We've got attribute names and corresponding types. The student ID is an attribute name, and the type is a UUID. And if you guys know what's going on, like this makes sense. A heading is this connection between names and types. A tuple everybody laugh at me if I say tuple ever again. It's the wrong pronunciation. I have a hard time with it, and I want people to laugh at me whenever I say it wrong. It's tuple. Tuple is the correct pronunciation. Rhymes with couple. Tuple. Don't say it the other way. I will probably at least once make that mistake today, and laugh at me, please. So a tuple is a set of attribute names and corresponding values. So this row here is the representation of a tuple. We've got, this isn't necessarily a student ID. We don't necessarily know that if we just look at that tuple in isolation. But we've got this is a set of all three of these attributes and their corresponding values. So we have a student name, Bob. We've talked about something here. It's like, hey, this row represents this tuple that represents an individual. We've got some surrogate key and their name and their birthday, and now we've learned something about this entity that we're modeling in the real world here. And so a tuple is kind of representing some entity in the real world. Typically, that doesn't always have to be an entity in the real world or whatever, but that's what a tuple is. And so it kind of corresponds to a row, but it's not the same as a row. A relation is a set of tuples that all share a heading. And now we've got this is a relation here, kind of two, this is a representation of a relation of two different tuples, two different people, Bob and Sally. We know things about them. And so a relation is a set of tuples that all share a heading. And like, if we just had Bob and Sally and there were different things that you knew about things, like you've got a movie and you've got an actor, those aren't sharing a heading. And so it's like, well, what does this really mean? It's not a relation if you're just combining two random tuples together that don't share a heading. A relation, now we're getting into terms that are a bit deeper. But a relation variable is a variable that can hold a relation. So we've got a variable, and we talked about variables are things that hold different values. A relation variable is a variable that can hold different relations, and maybe it's going to hold different relations at different points in time. I'm going to go into a little bit more detail later on this, and sometimes that's shortened to relvar. Relation variable is annoying to type out. Relvar is a lot faster. There's no distinction in what these things are saying. And because this is a presentation ostensibly about normalization, we're 25 minutes in and we haven't talked about normalization really yet, but it's a mathematical process to improve database design, specifically relational database design. Okay, so I talked about variables earlier, and the value of, everyone knows this, the value of a variable can change over time, right? I got JavaScript code here. I think it's the most common programming language in the world. More people know it than anything else. You see, hey, I declare a variable of type, a variable foo, I assign it 0, and then later it's 5. Foo isn't 5. Foo is a variable that has different values. Foo at one point in time had the value of 5, but at a different point in time it had a value of 0. Foo is a variable. The value of that variable, so it's a reference in memory or whatever, there's a lot of different ways to think about a variable, but the values change over time. And it doesn't matter which language you're using and what types of variables you're talking about. So in Python here, I created a set. We talked about mathematical sets earlier. We created a set and it has the values 1, 3, 5, and 7 in this set. And then later I changed it to a different set, the value is different. And then later I added something else to it. And if you want to talk about references versus value types, that's not what I'm talking about here. But at different points in time, favorite numbers had different things in it. It's a variable, it varied over time. And so in SQL, we can create a table called students. And a table is not a relation. And I'm going to go into a little more detail here. But if we say, hey, look, it's got these two columns, and then we're going to insert into a value to it. It changed. The student's variable changed. It used to have no items in it, and then it had an item in it. And then I updated it and I changed it to being something else. And so over the course of time, the student's variable changed. And we don't talk about this very often in software engineering. We don't think of tables as variables, but they're variables in more ways than one. And so I want to emphasize that a table isn't its current value any more than a variable is its current value. We sometimes say in the shorthand foo is 5, and there is some truth to that, just like saying the table has these things in it, but remember that these things change over time. And so I also want to talk about in a bit more detail that a table isn't really a relation variable either. It's a representation of data that might be relational. But in order to understand this just a little bit more, we've talked about how a set is an unordered collection of elements. I'm using Python syntax here, which might be a little bit new to some of you who aren't familiar with Python, but an array, a table, and a list, they care about order. These two arrays are not the same because they have even though the elements in that are all the same, the order matters, and you wouldn't confuse those two. Maybe this is a priority or a priority queue of things that need to happen in a specific order, or whatever order matters with arrays, tables, and lists, but not with sets. In a set, there's lots of different ways of presenting this data. 1, 3, 5, 7 is 7, 5, 1, 3. These are the same set. Mathematically, they're the same because the order doesn't matter. And there's other ways to express this. If you're familiar with lambda calculus or whatever, you're like, hey, I like this representation better. You can like whatever representation you want. They're the same thing. We're not going to talk about the value of representations here today, but I want you to remember that sets don't care about order, and tables do. So if we look at this is a table, and we've talked about earlier how this is a table, but this table is a presentation of this information. This table literally has an order. This kind of has an order. I presented this set in a way here, and it's different than this set. The presentation is different. You can see that they're different by comparing the pixels. But the table has an order, and when you're in a relational database, they're going to be stored in an order, and a table is just a representation of some set of data. And so a table isn't really a relvar either, because it's not a set, because the order does matter and has consequences. But more importantly, SQL tables aren't even presentations of relvars, because there's a few things that are weird about SQL tables. There are a lot of problems with SQL, and that's why I can very easily say that your favorite DBMS sucks, because if it's SQL related, it sucks, because there are a lot of problems with SQL. It's ubiquitous. Learn SQL if you're a student. I'm not trying to say SQL is a horrible thing to learn. I consider myself very proficient in SQL, and you should be too, but just remember that it sucks for a lot of reasons. One thing, duplicates are allowed in SQL tables. If you can have duplicates in a row, it's not a relation. It can't be. You can make a SQL table that stores this kind of a thing. This is exactly the same GUID. Feel free to double check if you care. This is exactly the same tuple. It's twice. And so because a SQL DBMS can store this, it's not a relvar. But also, this is null. There's this concept of null that you're going to hear about, and I hate nulls. Avoid nulls. Sometimes you have to have nulls, but avoid nulls. Nulls suck. We're going to talk about that a lot. And because you can store this kind of a thing in SQL, it's not relational. However, I am going to point out, there's also non-atomic domains, and we're going to go into a little more detail about that in a minute. But the fact that duplicates are not allowed is uncontested. You won't find anybody who says this is a valid relation, unless they don't know what they're talking about and don't have any formal training, and we're not worried about them. But these other two are contested. Some people think that you can have non-atomic domains, and some people say you can have nulls and still be relational. It's contested, and so we're going to talk about these in a bit more detail. So nulls. We're going to talk about nulls first. What is null? When you've got a null in your database, what does it mean?
Lack of value.
Lack of value. So it's not a separate value? Is null a value or not? You're saying it's the lack of a value.
You can search for nulls in an SQL database, but doesn't have a string or language or character or anything like that.
Yeah, it doesn't have a value.
Yeah.
And I think that's one of the perversions of nulls, the biggest. If you made null a special value, I wouldn't be having this slide today. It would be a little bit annoying, mostly because there's this 3-valued logic thing.
I would argue it's stored as a lack of value, but it is often treated as a special value.
Yeah, there's a bunch of really weird things going on here. Like, to that point, what is null and null? Well, that's obviously null, but does that make sense? Should that be null and null? That's partially what the 3-valued logic thing here is. But does null equal null? And to Philip's point, if you say that it is not a value, then null does not equal null.
But they'll match in databases. It depends on your database.
It depends. It depends. Why does it depend? Some databases, some DBMSs will say true, and some will say that the value of null equals null is null.
Right.
But then if null equals null is not true, then does the identity property not hold? And how many things break down when the identity property doesn't hold? I am not myself all the time.
And there's a difference between a null and a null string too.
Yes, in some DBMSs especially.
Yeah.
And so nulls are a perversion, and people kept loving this perversion and making the perversion worse. If null was just a special value and they consistently treated it as a special value and it had a value and null was always equal to null, then a lot less weird things would happen. And much smarter people than me have given hour-long presentations on the perversions of null, and I'm not going to go into all of that today, but there's a plethora of things that could be talked about there. What?
Just a plethora.
A plethora. A plethora of presents? Oh, so also because of nulls, some database optimizations are inconsistent or impossible to make. Because of the presence of nulls, the query plan, that when the database is trying to build what's going on, if there's nulls, then whether or not it optimizes can determine whether it can change the outcome of the query plan. And so you can get, and not just that, but it can change the output of the variables. And so when you have nulls, it's impossible to perform some optimizations. And I can point you to some papers where we talked about that in more detail, but nulls are a perversion and it causes a lot of problems, so avoid nulls. But it also makes human reasoning a lot harder, because then you're having to think, wait, it's not a value. Null doesn't equal null. Oh, did I use is null correctly in my SQL query? Did I do equals null or did I do is null? And just thinking about all these types of things is a cognitive roadblock that engineers have to deal with. And we don't want to make them do that. So when we're going to talk about normalization soon in a lot more detail than we have been, but it's harder to make sense of normalizations if there are nulls, and so that's why it's fairly core.
Can you go back one slide?
Yeah, I can make these slides available online too if you'd like.
That'd be great. Yeah, sure.
So the next is about domains, and we talked about complex domains. And we talked about Edgar Codd, who in the 60s hated DBMSs, and he thought, he complained about databases and thought databases sucked back in the 60s. And he's generally considered the authority on the relational model. He created it, and people treat him in many ways like a prophet, because like, oh, well, this is what Codd said. And he's dead, and so we can't ask him and what was really meant anymore, and he's been dead for a couple of decades. But people treat him with a lot of reverence for a lot of good reason. I'm not trying to say that he's a horrible person at all, but we're gonna look at what he said, because what he said about non-atomic values, people twist in some cases. So one of the things he said is a domain. We talked about domains are a data type. Remember, domains whose elements are atomic, that are non-decomposable values. So we can talk about 6, and he would say that 6 is non-decomposable. And if you're familiar with binary math or whatever, you might find ways to decompose it. But what he said was domains whose elements are atomic. An atom, even like a hydrogen atom, can be taken apart. So, like what atomic really means is a bit fuzzy, but what he says, it's not decomposable. Another thing he said is values that cannot be decomposed into smaller pieces by the DBMS, excluding certain special functions. And so it's like there's a lot of discussion about, well, so can that, people have taken these two statements to mean, well, if you can take it apart, then it's not, then it can't be the valid domain of another thing, the valid domain of a tuple. But he also said that each item in a relation is a simple number or a character string. These are things that he said that you can store numbers and character strings in databases and have it still be atomic. But a character string is a packed array of values. I know how to take apart a character string. They are decomposable, and we do decompose them all the time. And DBMSs have tools to decompose strings. So what does that really mean? And that's interesting. So I went to the library, and I read these books. I didn't read cover to cover all of these books, but I went through first normal form in all of these books and read all these things at the library. And these are some of the best minds in database theory, and there isn't a whole lot of full agreement about what the first normal form is, because there is disagreement. However, there are some general agreements. Every single one of these books believe that if it's a relvar, if it's a relation variable, it's in first normal form. Otherwise, it is a non-first normal form thing. It hasn't been normalized. As soon as it becomes a relation, as soon as it is a set of tuples, and as soon as the tuples are sets of attributes and they correspond with a header, as soon as you have a relation variable, you're in first normal form. Everyone generally agrees with that. What that means, though, is a little bit different. But in, I think, all but one of these books, nulls aren't allowed in first normal form. If you have a null, your database is not normalized. You do not have a relation. But yet, I bet all of you have seen nulls in databases that you've used. In fact, I would be surprised if any of you have used a database where there were no nulls. And I'd love to hear it. Anyone?
I built my own little project.
And you didn't have any nulls.
I built it so it doesn't have nulls.
Yeah, you built it because building nulls is hard,
Yeah.
right? Building nulls is hard. Somehow, SQL DBMS developers have decided, well, I'm gonna make this work. And they put a lot of effort into making nulls work. And until you've built your own and like, oh my goodness, that's a pain, I don't want to support nulls. That's the natural way of doing things. Nulls aren't allowed in first normal form, according to all these books. Also, some people talk about how if you have a table with a favorite color 1, favorite color 2, favorite color 3, a lot of professors have said, well, because you're repeating the columns, it's not in first normal form. Every single one of these says that that's allowed. That's not a restriction. You're allowed to have column 1, column 2, and column 3, and have that be in first normal form. But that doesn't mean it's a good idea. I want to be upfront about this. We're going to talk about normalization in a lot more. We're going to be going through this, but normalization isn't the only thing that matters in database design. It matters a lot, and it's something that you should definitely strive towards. But there's going to be other things that matter here. So don't have nulls, but also don't have repeated columns, even though it's technically still normalized. Okay, so what data types are allowed? This is the other part of first normal form. And COD specifically allowed strings and numbers, but is date more or less atomic? Yeah?
Actually, I have a question before that.
Please.
So, like, if you can defrag a drive because it's fragmented, and we're talking about normalization, what's the term for just non-normalized, or is there another term for it?
Yeah, that's this NF squared. Non-first normal form. I don't like this use of squared, but this is the term that they used. Non-first normal form. It is not a relation. It's a table. Still, you can call it a table, but you can say it's a non-relational table. That's probably what I would refer to it as, which basically means all these RDBMSs like MySQL and Postgres and Oracle and the SQL Server and DB2 and Linter and all of these DBMSs aren't relational. Now, some people call them pseudo-relational as a result. But those are mostly people who are highfalutin and really love the relational model more than other people. Everyone else just calls them relational databases, even though they aren't storing relations. Okay, so the question is, thank you for that, great question. But strings and numbers are allowed, according to COD, are dates more or less atomic than numbers. Or sorry, more or less atomic than strings. I don't know. Like, some people say that you can't have a date, or you can have a date, and like, because the date you can take apart dates. You can have months and days and years, and there's different components. Is that allowed or not? There's also things like, well, COD implied that having an array of something means that if you, like, my favorite colors are blue and green, and that's the set of favorite colors that I have. And if you put the set of favorite colors, then now you've got something that definitely can be broken down. And it's implied that that's what he was talking about, that you can't have a set of things or a list of things, an array of things, as the data type for a column. And he implied that. But he also said that strings were okay. And strings are an array of characters. So it's not clear what he was really saying. And as a result of that, there are a lot of people who think any data type you can define is allowed in first normal form. Like, you're even allowed to have relation types. Like I've got a column called favorite colors, and it's a table or relation of, well, green since 2025 and blue before that. Like, you can have complex, really complex data structures. And there are some very respected database theorists who say that's okay for first normal form. And I can see where they're coming from. But I can also see where the other people are coming from. I tend to lean on this side here more than the other side, but maybe that's because of how I was raised, and I can't separate my biases from what's really going on. So let's talk about what you should do to actually get there. And so to get to first normal form, if you have how do you get there? Well, if you have a truly relational DBMS and not one of those pseudo-relational SQL things, then congratulations, you're first normal form. You can't do anything otherwise. But that's not most of us. I haven't worked on a truly relational database since I worked with him, was that 20 years ago? Okay. Again, I feel old. And so if you have a SQL DBMS, well, what do? Always add a primary key. If you don't add a primary key and I see your database, I guess depends on how senior you are. I'm going to be talking to your manager about training that you're going to need to be going through. And if you're a professional who's been working for a very long time, I may try to get you fired. This is a really big deal. Add primary keys to your databases. Otherwise, you're not in first normal form. And every one of those books agrees with me. First normal form matters. Now, if you're, I'm talking if you're building a relational database or a pseudo-relational database. If you're building a Redis DB and you're doing other things, there's exceptions to this. We're talking about in relation land or even pseudo-relation land. Add primary keys. Also, unique constraints, technically speaking, that makes it conceptually a primary key, but unique constraints are important too. This is kind of the same thing. If you avoid a primary key, then that's great. There's other ways of doing non-unique indexes, but these are all conceptually the same concept. We talked about keys a little bit. I'm going to go into a little bit more detail. This is like a legend, like a legend. A key references something else. It's a way to look up information, and it's not like a lock key. It doesn't unlock things. Even though I'm going to use, even you saw me using the key icon, and I'm going to use that later. It's a different definition of key, but there isn't an emoji for a legend. Hey, wait a sec. If you guys have been paying attention, you notice that I didn't talk about domains because I was intentionally avoiding it. And so this is recommendations. I can't do more than recommendations. I can tell you what I think is a good idea, but I'm going to give my recommendations here but there isn't papers that I can point to say, well, this is really the best way, and I think this is the best way, and I can't prove it, but eliminate nulls wherever you can. Not null by default. Saves you a ton of traps. And it's a good exercise to say, well, how would I build this without nulls? Because everything can be built without nulls. I've never seen a database structure that can only be built with nulls, but sometimes it's not necessarily worth the effort. Definitely avoid it. And also avoid complex types. If you want to have relations, you can stand on some high horse and say, I put relations in my tables as data types, and I'm still normalized. Sure, but that doesn't make it easy to do. Avoid complex attributes. Sometimes you want them, sometimes you need an array, and if you want to, that's fine, but keep normalizing anyway. The documentation in the literature says, well, you're not in second normal form unless you're in first normal form. And if you say, well, I put a null and I put complex attributes, no matter who I look at, they're gonna say it's not first normal form, but still go through the other normalization steps anyway, because those other normalization steps still have value. So these are my recommendations, but don't let that stop you from going to second normal form, even though technically speaking, you're gonna have some difficulty. So, second normal form. This is the formal definition for second normal form. Don't write it down, you don't need to take a picture. This is not important because this is really complex. This is a semester in a database course to really understand what all of these things mean. I haven't, but also I crossed off that first one. Remember, it's first normal form, it's a recommendation being in first normal form, but that's not really important for most of what we're talking about. There's still a lot of value in second, third, and fourth normal forms. So ignore that rule, that's an optional rule sometimes. But I'm not gonna talk about what a prime attribute is, or a functional dependency, or a candidate key, or proper subsets. That's not database specific, but I'm not, this is a really complex rule that you will probably gain some edification if you understand them. And Adam was talking about how he took a course and he's like, oh yeah, prime attributes, maybe this is triggering for him. Because these are weird concepts that you have to understand for the test, but I'm gonna give you a shortcut. And you may not be able to pass a test with this, but second normal form is everything should depend on the whole key. That's a good, simple rule. Everything should depend on the whole key. So let's talk about what that means. Before we go to that, why should we be normalizing here? What value do we get from further normalization? And on the second slide, I talked about what bad design was discovered. They wrote proofs to say these are problems that it has if you don't normalize your database. And so I'm gonna highlight two of them here. Additional restructuring is needed to add additional data. How often have you needed to make changes to columns or add new tables to a database structure as you're moving along? In the industry, this is what I feel like I'm doing most of my time. And well, I've got to spend a new database. I've got to redesign I've got new data that's coming in. How do I store it? I mean, you have to add new tables and if your data is normalized, this step is easier. This is good design. If you normalize to, I'm going to say fifth normal form, you will get better design and it will be easier to make changes. And if you're writing throwaway code that you're not going to care about later, then that doesn't matter as much. But if you're going to ever need to update your database to add more data because business requirements change, they do, normalize your database. It's going to make your life a lot easier. Jeff is just talking to me yesterday or 2 days ago about how much pain he has to deal with because he wasn't normalizing his data. I was like, well, you should have called me before.
And you can translate pain into it's expensive.
Yeah, and this is a monetary expense. It takes longer. Convince your bosses that it's worth the effort if they're ever going to make changes to the data structures.
I just thought I'd give you an example that we're dealing with right now.
Okay.
So we're a startup and we have a fintech partner, and a key component of our offering is that we market primarily to Spanish speakers. And our fintech partner is very on board to collaborate, but they do not have a mechanism to control whether or not the customer is a Spanish speaker or identify their language. They have no marker for it. And so they're having to go back and reformat, and it's delaying a collaboration because of this. And so it's a big deal because it's costing them a lot of money. They can't allocate resources. They can't account for how many of their customers speak which languages because they didn't initially build it in, and they must not be normalized.
And there could be other reasons. It's probably,
Yeah.
I'm not going to insist that it's normalization, but it's bad design. And if there's one thing you can take away from this, that the quality of your code matters in making it easy to change later and to deal with later. Good design matters. And normalization is mathematical principles. We can prove the design is better or worse than things that aren't because of these types of problems. And yeah, if you're not designing a database and somehow you need to support multi-language stuff, it's going to be a lot easier if you're fully normalized, and you might not be. Data anomalies are another thing that I'm going to point out here, where sometimes when you make changes, you have to make changes in more than one place. And if you've got if you're dealing with transactions, or if you've got concurrency types of concerns, then it's going to be harder to prevent these data anomalies if your data isn't normalized. And one thing that matters here is one fact in one place. If you have one fact in two places, you have a problem. And that's a lot of what database normalization is about, is simplifying these one fact in one place types of things. Okay, so second normal form. This is a table. I had AI make this table for me. And this is a presentation of data. And if you really want to know more about Christopher Lloyd, you're going to want to come to my next presentation next hour, where I talk about the Klingon language, and it's going to be awesome, and it's going to be a way different presentation than this. Okay, so this is a table, and I have seen reports that look like this, presentations of data that look like this, and this is a presentation of data. This is not normalized. So the first thing we need to do is we need to identify the keys. Who can see what the keys are in this table? This is, do I need to is the table understandable well enough? Is there any weird questions about what's going on? I'm asking this is an exercise. Maybe I should just tell you because of time constraints. But we have, in this particular table, I use a key logo here. Again, it's not the right definition of key, but there isn't a legend or a lookup emoji. So movie and actor together are the key. And it's not that there's two separate primary keys, that the key combined, that you have to have both of those two together it's a composite key. Otherwise, the table doesn't make any sense, but you can't have more than one actor on a movie because that's how much we're getting paid and who their talent agencies, we've got all this information here. But this data isn't normalized. And so what data here, we're talking about, it has to depend upon the whole key. What columns here don't depend upon the whole key?
Movie director.
Doesn't this depend on the whole key?
It doesn't depend on the actor.
It doesn't depend on the actor. That's right. This movie director column doesn't depend on the whole key. What else do we have?
Director's salary.
What?
Director's salary.
Director's salary, right? That depends on the director. What else?
Actor's agent.
Actor's agent depends on the actor, and it doesn't depend on the whole. There's other things here, but we've identified them, and so we can take the steps to decompose. In this one case, I made one decomposition by pulling out all the actor information. I also made a surrogate key because I think surrogate keys are a good idea, and I think they're good design, but they're not part of they're not part of database normalization, but it's part of good design for reasons we're not going to go into today. And notice I had it come out the left and into the right, mostly for space reasons. I'm following the Alphora style. I don't draw it up because this is a one-to-many relationship, because a person can be in more than one movie. For example, we've got 4 here twice. Because I specifically picked Christopher Lloyd being in both movies, partially because he speaks Klingon, and that's not what we're talking about right now, though. Another decomposition here is we're going to pull out the director stuff that got mentioned, and so we pulled out the movie stuff, the director stuff we're going to talk more about later. But now this is normalized to second normal form because we pulled out these things and the keys here. All of this data now depends upon the whole key. Spock isn't directly corresponding with the actor. It also matters what movie he's in because Spock might be playing in other movies and other types of things. So this data is not dependent upon the actor, and so now we have this database that is now in second normal form. So third normal form, you guys know the drill. We're not going to talk about transitive dependencies or candidate keys or functional dependencies because we only have a few more minutes. And so I'm going to give you the shortcut. Everything should depend on nothing but the key. And if you're following along, the rule for third normal form is everything should depend upon the key, the whole key, and nothing but the key. So help me God. Okay, so the third normal form, everything should depend on nothing but the key. So let's look at this here. First, what are the keys? It's not gonna be an exercise here. We've got a 2-part key here. And is this part of the key? we're not going to talk about that today because that's a complex thing. What happens if somebody is portrayed more than once in a movie or portrays more than one actor? We're not going to talk about that. We've got 2 different keys. Thankfully, there's 2 different key emojis, so I could just do it like this. And so the person ID is one key. The actor name is another key. Also, we've got movie title and movie ID as separate keys here. We can identify data that doesn't depend upon the whole, it depends on nothing but the key, which in this case is the director's agent depends upon the director's name, which isn't part of the key at all. And so we need to decompose that. So the full decomposition to third normal form looks like this, where we now have the movie information. There is a director, and the director references there all the director information. Make sense here? We're still on the same page? There's also a normal form called Boy's Codd normal form. Again, there's a distinction between third normal form and fourth normal form, but it's basically the same. There is a distinction. We're not going to go into that detail. Still depends on nothing but the key. We're not going to talk about the difference between a trivial dependency and a composite dependency. Not relevant. There are higher normal forms, and I recommend getting to fourth and fifth normal form. And the rules there are a bit more complex, enough that we can't get into them because we're not going to talk about multi-value dependencies or joint dependencies here today. But mostly this is when your data is really complex and you're trying to shove stuff into more than one table. So really it's use lots of tables is the recommendation. And especially be wary about data that's depending upon a composite key. You're going to have data that depends on a composite key. You can't avoid that. But you want to make more tables. And so, is this the best design for this data that we have? The answer is no. We've fully normalized this. This data is in fifth normal form, but it's not the best because is one fact in one place? And we've kind of gone through some of this kind of quickly, but if you're looking around, it's like, well, Leonard Nimoy got paid $3,500,000, and for being an actor here, but he also, that's McCoy, that's not Leonard Nimoy, Spock. This is Leonard Nimoy got paid $4 million. He was the director on Star Trek 3, but he was also an actor. So he's in both of these 2 places because he did he get paid $8 million or $4 million? This data doesn't tell us unless we know more about the data. I can't tell you whether or not a fact is in more than one place because this data doesn't tell us. Also, he is represented by United Talent Agency. Is that because was he represented by the same agency because of who he is, or does he have could people have separate talent agencies because they for them being a director and for them being an actor? This database doesn't tell us. This presentation of the data doesn't tell us. The database needs to know that type of a thing. And looking at this, we can't know the answers to those questions. So I can't even tell you whether or not more than one fact is stored in more than one place because it might be a different fact that he got paid $4 million as a director than that he got paid $4 million as an actor. I don't know if these numbers are true. I made them up too. I'm not saying how much he got paid. So I don't even know if this is one fact or 2. And you need to understand that as part of your database. Only store your data in one fact, in one place. I drew circles instead of, But so this is not the best. And I do want to say that there are other factors that matter. And so database normalization is an important step, and it's a step that you can prove is a mathematically great idea for good design. But there are other non-normalization optimizations to have better design. So design your databases, make them as relational as possible, and you will prevent a lot of traps. And I guess that's everything. Thanks for playing. Anyone have any questions? I'm over a little bit. The next presentation is in 10 minutes, is that right? And I have to run in about a couple to get set up over there for my presentation on Twitter.
Where should we go to learn the next step?
What's the next step for you?
Well, I don't know. So, like, if you had another hour on the topic, where would we find that material?
It depends a lot on. You want to speak about that?
And
I don't know.